Okay, I thank the organizers for bringing us all together. Yes, actually, I apologize for confusion. I sent the first title, which is in the book, but then decided to change it since I thought this would be more appropriate for the session. But I'll actually still add a few slides related to what I advertised in the booklet. So, because it also connects to what I'll be discussing in this talk. So the work that I'm presenting today is motivated by what we heard from Andrea, analysis was done in collaboration with several people. So in particular, the first part was really primarily done by Mertash Babadi and Michael Knapp. And then the later part, which has to do with more variational states, which I'll discuss at the very end of my talk. So here the main credit goes to Tao and Ignacio Sirac. Okay, so this is an outline of my talk. I'll sort of skip the introduction, more or less, just reminding you about the experiment, since we had beautiful lectures early on. I'll jump right into, say, simple physical arguments why we think that this effect of enhancement of electron-phonon interaction in non-equilibrium systems can be generic, how we can then use this to analyze transient superconductivity, and then finally I'll say a few words about how we plan to study properties of this transient superconductor, and this is work in progress, and this will rely on this kind of non-equilibrium dynamics studied with variational states. Okay, so this is what we heard from Andrea, right? So this is a buckyball superconductor. They excite phonons, and they see signatures of superconductivity at very high temperatures, which is temperatures which are much higher than equilibrium TC. So what I'll try to show you is that we think that this is a generic phenomenon that if it doesn't really rely on anything special about buckyball superconductors, and that's why we will focus on something as simple as a Holstein model, because if we think it's a universal phenomenon then, and generic phenomenon, then it should be present even in simpler models. And of course, we're not the only people thinking about this experiment. So many people in this room who have done very interesting work, but I'll be very selfish and focus just on what we have done. And also, I will not discuss, let's say, what we heard about similar experiments in high TC Cooper rates and possible applications to other types of ordered states. So first of all, let me remind you why gaining from a non-equilibrium state, gaining, let's say, high TC from a non-equilibrium state of phonons has been considered kind of a fool's errand. So kind of there is a very canonical argument which says that actually you really need virtual phonons rather than real phonons. So it doesn't matter which state of phonons you can create, you cannot increase TC. So roughly the argument is as follows. So let's go back to our usual perturbative calculation for the coupling constant, right? So it's second order process. Two electrons come in with momenta k and minus k. Then let's say a phonon is emitted by the left electron. And then we get a pair of electrons at p minus p. Let's try to calculate matrix element of this process. So we have matrix element squared. Let's say we look at a state where we already have phonons. So then the matrix element, instead of 1, you can say we can have both enhancement factors. So we get 1 plus n. And then we'll look at energy denominators, right? So the transient state now has electron at p and the phonon frequency at and an extra phonon. We have to subtract the initial energy of electron. We're typically interested in electrons near the Fermi surface, so we set like all these energies, electron energies equal to 0. Okay, and it looks like we get an enhancement in this diagram if we have a finite occupation number of bosons, right? So we have an attractive contribution, which seems to depend on the phonon number. Well, but then if we have finite number of phonons, we should also consider a different process when when the phonon is not emitted but rather absorbed. And now intermediate state has one phonon less, right? And now the matrix element has the number of phonons in it. So now we have actually repulsive contribution proportional to the number of phonons. And so if we add the two up, we see that effective interaction actually the n-dependent part cancels, and we just have, the usual matrix element squared divided by phonon frequency. It doesn't seem to depend on the number of phonons, and that's why people believe that, you cannot really enhance superconductivity by playing with the non-interacting state of phonons. So how can we trick the system? Okay. Now, let me consider a different philosophy in a sense when I'm not thinking about the state, non-equilibrium state of phonons, but rather phonons which are driven out of equilibrium. And specifically, let me consider a model in which, let's say, if we think about phonons as oscillators, the spring constant is being modulated in time, right? So it's like a parametric resonance, you see. So this is like the frequency of individual phonon mode, and it has a constant part plus some modulation, right? Okay, I'll explain later where this can come from, but let's just consider this for the time being. And now we can ask, okay, so we know how to calculate effective electron-electron interaction when system is in equilibrium state, but how would we calculate effective electron-electron interaction when phonons are in such parametrically driven state? So we want to reduce electron-phonon interaction to some effective electron-electron interaction. Well, actually, it's very easy to see that effective interaction between electrons induced by phonons can be reduced to the familiar response function of the phonons. It's as simple as basically the usual retarded correlation function for the phonon. So like this Q would be basically, it's like a displacement of the phonon. Okay, so instead of giving you a formal derivation, let me give you more of a kind of intuitive argument. So think about any system, right? Okay, in principle, we're thinking about oscillators, but this argument is more generic. Say we have a system which is described by the Hamiltonian H, and then we couple some external field phi to the operator of the system, right? Q. So Q in our case, right, is a phonon displacement. So we know that when you couple external perturbation, right, then you will induce the response. There will be expectation value of this operator Q, which is proportional to the external force through the response function. And it's the same response function which determines fluctuations in the system. That's the usual fluctuation dissipation theorem. And it's also the same coefficient that determines how much the energy of the system is lowered in the presence of this external field. So now if we go back to our system, well, so Q is this operator, right, displacement operator for phonons. So from the point of view of the phonon oscillator mode, we can think about some external operator, which is really like the density operator for electrons, right? And this is coupling to the oscillator mode. And so by this argument, we know that, okay, so the extra energy should be proportional to the square of the external field. And in this case, external field is just an electron density operator squared. So this is our electron density squared. And the response is the response function, right? So therefore, if we want to get the effective response function, if we want to get effective electron-electron interaction, just have to calculate response function of phonons out of equilibrium. Okay, that's actually not so hard to do, because even though it's a time-dependent problem, fortunately, it's just a harmonic oscillator. So this is linear theory. We can just say write equations of motion, right? So we know that the evolution of Q of displacement, the conjugate variable momentum, they're related to each other. Now the frequency is time-dependent, right? And we can solve them. And so what we can do, we can, for example, relate displacement at later time to displacements at earlier time, and let's say conjugate variable at earlier times. And so therefore, if I want to calculate response function, I just have to relate. So if you remember, the response function, it's right, is a correlated of operators, displacement operators at earlier time and at later time, right? And I just have to basically relate my operator at later time to operators at earlier time through this propagation kernel, and this gives me a response function. And notice that this propagation kernel, right, something that gives me relation between, say, displacement at later time and earlier time, does not depend on my initial state. These are linear equations, right? It only depends on the Hamiltonian, which controls dynamics of the phonons. Therefore, this response function, right, which gives me effective electron-electron interaction, doesn't depend on the state of phonons. That's consistent with what we learned before. However, it does depend on what is the equation that describes dynamics of the phonons, right? So therefore, by what I want to rely on is not a non-equilibrium state of phonons, but rather a non-equilibrium Hamiltonian of phonons. And in particular, what we want to play on is the fact that, well, we're used to the idea that close to phase transition response functions, close to equilibrium phase transition response functions can be large, and that's why close to phase transition superconductivity often appears. Now, when we talk about parametric resonance, we know that response functions can also be very large, just because the system is very close to being unstable, and that's something that we want to utilize in order to enhance response function of the phonons, and therefore get larger electron-electron. Yes?
So what is the distribution function of phonons? Do you assume that it's...
I'll calculate it.
Oh, so it is non-equilibrium.
It is not. Sorry, this is like a toy model just to explain. I'll show you like full non-equilibrium calculation later on. Okay, so now, again, just going on with this simple argument, we can, let's say, do perturbative calculation in the drive and see how interaction strength is affected. And again, as we expect near the parametric resonance, when we drive the system so that it's very close to being unstable, say, we get strong enhancement of both the, say, the time averaged part, right, plus the oscillatory part. Because obviously, if we modulate at finite frequencies, then our response function is also modulated. But actually, again, the fact that our interaction is modulated in time also works in our favor, because if you remember, BCS is a very nonlinear function of the interaction, and therefore you gain much more from enhancement of interactions than you lose from suppression. So again, you can just formally see it if you do even that when we think about naive averaging of the BCS coupling constant, then of course we have to average the exponent, and it's not the same as the expectation value of, say, then exponential of the expectation values. Okay, so this is, Victor was saying, okay, this is very simple. Let's do something, we need to do something more reliable in order to see if this argument makes sense. So now, as Andrei explained to us, there are several stages in the experiments, right? So there is a pulse which excites infrared active phonons. These infrared active phonons exciting Raman phonons, which are primarily coupling to electrons in a sense of which are primarily important for giving rise to superconductivity. So we're not going to look at all of this. We'll basically start the problem from here. So we'll only discuss Raman phonons and how they couple to electrons. So we'll basically treat these infrared active phonons after they were excited as a source of classical drive. So we assume that they keep running for a long time. And also, the focus will be on really things which cannot be captured by effective renormalization of static theory. This is probably important in real experiment, but we want to focus on things which are really new. Okay, so this is the Hamiltonian. So these are our electrons in the Nambu notation. These are our phonons. And again, I remind you, this is just Raman phonons. So we consider some nonlinearities just in the phonons themselves. The reason we need them is because our, let's say, infrared phonons, like so this F basically, T squared is like a square of the infrared mode. So it's excited at Q equal to 0, therefore it's primarily exciting, it's really just exciting Raman phonons at Q equal to 0, but we have to transfer this drive to phonons at all finite wave vectors, because we know that superconductivity really comes from phonons at large momentum. And then, as I said, we take a very simple model of electron-phonon interaction, just the usual Holstein model. And okay, so and then we so there is since we are going to look at the driven system for phonons, and of course we need to include dissipation. So there is this part of the dissipation which will be included just because phonons are coupled to electrons. So that's part of the analysis. But then for q equal to 0, because electron, you see that the way we write our interaction, we're coupling to density, and we know that at q equal to 0, electron-phonon interaction is screened completely, or Coulomb interaction. Therefore, let's say the damping would be absent, so we have to add extra dissipation at q equal to 0. But for finite q phonons, most of the dissipation just comes from electrons. Okay, so now this, let me just give you a sort of rough idea of the kind of calculations that we're doing. So let's try to understand what's happening to phonons. And for phonon, we're really driving q equal to 0 part. So this phi is an expectation value of the phonon field at q equal to 0, right? And you can see that the first term would be just the usual kind of just shows that we have an oscillator, right, with some finite damping. Then there are nonlinear effects. But then there are also, and this is a driving force, but then there are also effects of coupling of q equals 0 phonon to finite q, right? And for finite q, of course, the phonon couples not to the expectation value, but rather to some to the correlators. And then we have to write an analogous equation for finite q of phonons. But for finite q phonons, we cannot get expectation value of the phonon field. We can only get correlations. We can get which we encode in the Green's function, right? So again, you see the first term. This just shows that we have the usual harmonic oscillator, and then we have, but then we see that there is a drive acting on the phonons, and this drive comes now from the q equals 0 part, from the fact that for the same phonon we have a coherent state at q equal to 0, and then there is damping coming from electrons. So okay, we have a problem which is time dependent, and so how do we want to solve it? So usually when we're dealing with non-equilibrium problem, it's common to just separate the time into kind of center of mass time and the relative time and do Fourier transform. And so this is the so-called Wigner transform. But in this case, it's actually it's not easy to do this because this transformation usually assumes that it's a function of the center of mass time. We just have evolution which is much slower than evolution as a function of the relative time. So in this case, however, we have a very fast driving, right, which is very at frequencies which is close to the phonon frequencies. So the way to deal with this is to actually extend this Wigner representation to Flaquet representation. We decompose dependence on the center of mass time into separate Flaquet components. Basically, you can think about it as just different Fourier amplitudes corresponding to sort of different harmonics of the driving field. So this is something that is used quite often, for example, in electrical engineering in the theory of signal transmission. And so people applied it earlier in the context of electron systems, but the assumption, then they would quickly jump into sort of thinking of like basically considering, let's say, electrons as sharply defined quasi-particles. So in this case, I believe it's the first time when we do a full quantum kinetic equation, which analyzes, for example, the smearing of the spectral function. Okay, so I think, Victor, that's what you were asking about. So this shows you, for example, the Keldysh function, right, for the phonons. And so this shows you that, well, okay, so this was maybe just taking one step at a time. So this is a displacement. So we drive our phonons. So it oscillates rapidly in time. We separate different Flaquet components, right? So different Flaquet components are now smooth function of time, right? So just amplitude itself is rapidly oscillating. And this is for finite K modes. Then we characterize this by, again, different Fourier, different Flaquet components of the Green's function. What's important to us is that actually can see that there is some frequency normalization. There is actually a softening of the phonon. So which, again, is something quite interesting. And this just shows you that it's also helping superconductivity, because you remember that effective coupling constant is G squared over omega. And therefore, if you renormalize phonon frequency, then of course you decrease it, you get high TC, but this is not such a large effect, so we'll need something much larger. And this is just higher Fourier amplitudes. But this takes into account the fact that, yes, due to, let's say, nonlinearities, now the spectral function is much broader. Right. So now that we understand phonons, we need to put this into the discussion of electrons, and we start with the usual Migdal, kind of the usual lowest order self-consistent diagram, right, which is kind of the basic diagram in Migdal-Eliashberg theory, and which basically tells us that dispersion of quasi-particles is renormalized by interaction with phonons. Of course, by interaction with phonons, also changes the coherent, gives a finite lifetime to electrons. So that's also a question that was asked earlier. So if we make an unequilibrium state of phonons, right, we're basically driving this system. We may enhance electron-phonon interaction. We'll see later on signatures that this is indeed the case, but we're also making electrons very short-lived. In the usual BCS theory of superconductors, we usually don't even worry about quasi-particle lifetime because the temperature is so low that there are no phonons around, and so electrons cannot really absorb existing phonons, and then they cannot emit phonons because of the Pauli principle, because also electrons are at very low energies. And that's why any kind of sketching of electrons is strongly suppressed. But once we're talking about non-equilibrium state, we have many phonons present in the system, so we no longer have this constraint. And therefore, like driving of the phonons, it can have some useful effects, which I told you about earlier, of enhancing electron-phonon interaction. But it also has detrimental effects in a sense of making electrons less coherent. So this is all included in this analysis. So far, we're not looking at anything which has to do with superconductivity. We're just analyzing. Let's take the normal state, electron-phonons, make an unequilibrium state of electrons. So what happens? So this shows you effective the electron spectral function. This is what can be measured, say, in ARPS. You see, so this is the king. This is the usual signature of electron-phonon interaction, a change in the slope. And this is before the drive was applied. So you see that actually near the Fermi surface, we have very sharp quasi-particle, essentially zero lifetime. Now, as we start driving the field again, so this drive corresponds to just like this infrared active phonons, exciting Raman phonons. You see that we start changing the electron spectral function quite dramatically. Okay, we get Fourier reflections of the quasi-particle peak. So electron-phonon interaction is enhanced. You can see it from the fact that the effective mass goes up, right? So the effective mass is, as you know, has the larger is electron-phonon interaction, the heavier is electron mass. So we get very large enhancement of the effective mass, and which is good, which is as what we expected. So we said, oh, non-equilibrium state of phonons is actually is increasing electron-phonon interaction, and that's good for us. But we also see the negative side of non-equilibrium state. Look at the width of the spectral function. It is now finite. Actually, electrons become very incoherent. And once they become incoherent, this, of course, is very bad for superconductivity. Therefore, non-equilibrium state of phonons does two things for us. It enhances electron-phonon interactions, but it makes electrons less coherent. And what happens at the end is a competition of the two. OK, so yes?
So is the driving frequency the smaller time-wise that we have the superconducting or larger?
So we assume it's larger. Yes, it's larger. Yes.
Okay. So, but then it also.
Actually, in this case, there is no gap yet. It's a normal state.
You want to get. So I'm guessing there was this Eliashberg theory of enhancement.
Yes, yes.
That it actually matters where you start, like in the superconductor.
So we will always start sort of like above the equilibrium TC in this analysis. You see, I will only look at the instability. You're running ahead of me again. I'm only analyzing instabilities at this point. But yes, again, the focus was more on this kind of regime where the frequency of phonons is still high enough that, for example, the assumptions of Migdal-Eliashberg theory work.
My question was actually, do you assume that the electron distribution function stays the same, or is also?
Come on. Okay, so that's what I explained. We calculate everything. We calculate how the spectral function changes, how the occupation number changes. Okay. It's all done, you know, the completely honest, you know, Keldysh-Eliashberg Fourier calculation. OK, so now that we understand the normal state, that's how we can ask whether the system is unstable to superconductivity. And reminding the usual BCS, it's pretty simple. You just say, oh, when can I satisfy this BCS self-consistency condition, right? I assume that I have anomalous expectation value, anomalous part. I add it to the self-energy, and I calculate anomalous part in the Green's function and require self-consistency. There's just one parameter, delta. Now we have essentially, it's kind of the same thing, except that we have many parameters. Like already in the usual algebra, you get an extra frequency dependence on delta. Right? In our case, in addition to frequency dependence, we get this Flaquet indices. We also get dependence on time, on this kind of slow time variable. So everything becomes a nasty matrix equation. Okay, let me not trouble you with all the details. So that's actually the very hard heavy lifting that Mertash has done, but this is the result. So basically, in unequilibrium states, we saw this effective mass going up, right? At the same time, the distribution is getting more smeared. Sorry, I don't have plots here, but yes, it is getting smeared. And that's kind of another reflection of the fact that electrons are getting less coherent. So here you can see that the incoherent part, the imaginary part of the self-energy, is getting larger. So that, of course, immediately would result in distribution function becoming less sharp. And now if we just ask when is superconductivity possible, so in Migdal algebraic theory, this is when the eigenvalue sort of becomes negative. This means that we can now allow for the self-consistent solution that has off-diagonal order parameter. We see that, okay, as sort of we switch on the pulse, it stays positive, then electron-phonon interaction becomes large enough, right? And so we get instability, but eventually the electron decoherence catches up with us, and therefore this kind of window of superconducting instability disappears. So we only have this transient instability to the superconducting state. So at this point, we're really just analyzing instability, right? We're not asking what's really happening inside once this instability happens. We're only asking, okay, so at which point, like, so what, say, was the initial temperature when you could have superconducting instability? So this, say, summarizes the results. So this is a color plot, and on the horizontal axis there is a frequency drive in this simple model. This is the amplitude of the drive, and we see that the largest enhancement is very close to where the system is parametrically unstable. So this gray region is basically a regime where we drive phonons so strongly that within the dampings that we gave to the system cannot stabilize itself. The phonons just really kind of like explode. And so this is color coding of enhancement of TC, so it can be as large as 150%. Now, again, what I want to emphasize is that to get this effect, we really had to put this Flaquet component. Remember that kind of the fact that this parametric resonance, that we were getting a squeezed state of phonons. So that was crucial. If we do not include it close to resonance, we actually get suppression of TC. That when we make electrons more incoherent, then we enhance electron-phonon interaction. So therefore, Flaquet aspects were crucial. Okay, so now let me move on to sort of the second part of. It's actually the motivation for the second part of really again comes from this experiment. So okay, we get this transient state, and we can argue whether it's true superconductivity or not, because clearly we're not getting long-range superconducting order. We get some kind of correlations. So what we should really do is compare the actual response function. And so as you can imagine, again, just for people who know some of this, let's say what we use is technically is called conserving approximation. So it's it's basically you write self-consistent equation, and solving them on the Green's function is painful enough. That was really very hard to get results that I showed you. If we want to calculate, say, optical response, this would require solving Bethe-Salpeter equation. It's really hard, at least, okay. Frankly, I don't see how we can do it. So we want to look for alternative ways, and now I want to give you another way of trying to approach this electron-phonon system. In particular, try to look at the response function. And for this, let me take a step back and sort of like just think about states which we're used to, states which can be described using the usual mean field theory. So actually, fundamentally, the ones that we use most often are nothing but Gaussian state. Like, say, if we take phonons, if we take bosons and we look at the Bogolubov theory of bosons, right? So we have a condensate at finite momentum. We have quantum depletion, right? We just have this kind of coherent pair, like again, coherent pairs of phonons at k minus k. Or if we take a BCS state of fermions, right? Again, this can be written as a Gaussian state of fermions. So in fact, essentially, a generic mean field state can be written as a Gaussian state, and this is a more general form. Let's see if I divide my phonons into, let's say, it's like coordinate and momentum operator for the phonons, right? I can write the part which is linear in this operator. So you see this R, basically something linear in B and B dagger, and then quadratic part, right? And then let's say coefficients that come in here, expectation value, and basically they describe correlation function. Or for fermions, again, Gaussian state is something where we put two fermion operator in the exponent. Okay, here I just choose to represent them using my Majorana fermions. And then if we have both bosons and fermions, the best we can do within Gaussian approximation is to just take a product of bosonic Gaussian state and fermionic Gaussian state. The wave function between bosons and fermions, it has to completely factorize. And that's just not good enough. So for example, if we take the Holstein model, within simple Gaussian states, they cannot see even a simple superconducting state because effective attraction between electrons is mediated by having some kind of entanglement between fermions and phonons. So the way to go around this kind of simple approach of Gaussian states is to do this kind of approximation based on what you can say is beyond Gaussian. So it really is an extension of what people defined before as canonical transformation. Here we just generalize them. Roughly the idea is that before you consider Gaussian wave function, you apply some kind of transformation, typically unitary transformation, which introduces entanglement. So in the context of electron-phonon systems, what you can do, you can entangle phonon and electron degree of freedom. But usually, when people do such canonical transformation, let's say what Dante was telling us about, this coefficient of the transformation is kept constant. But you don't have to. So in fact, the kind of version that we're exploring now is when you keep parameters of the transformation as still one of your variational parameters. It's also parameters that can depend in time. And now you try to, let's say if we are looking for the ground state, you just try to optimize this wave function with respect to both parameters of this transformation and the Gaussian state. And the way to do it, you say, oh, I can define a kind of a tangential plane. So I know if my parameters change, what are the basis wave functions that I can generate, right? So if I think about, so let's say it's a new part of the talk, so I don't have very nice slides yet. So let's say this is a manifold of the many-body wave function I can get using this kind of generalized sort of states which include canonical transformation and Gaussian states. If the system is somewhere in here, just by changing parameters, we know that we can describe a certain tangential plane, right? And we have certain basis vectors. So now what we do, we write dynamics in imaginary time, but generically, when you write dynamics, of course, it takes you out of this variational manifold, and then you just project it. You want to just look the part of the evolution in imaginary time, which leaves you in the manifold of your variational state. And you can use this to get a very simple expression for how your parameters change. And this is actually, turns out, it's a very useful representation. You can show that within this dynamics, the energy is continuously decreasing. So your evolution will always end at some at least locally stable point. You can still have several distinct local minima, but which you need to compare, but at least it sort of guarantees you to find kind of a very reasonable local minimum. And then what you can do, you can also generalize this to time-dependent evolution, in which now when we look at dynamics, we write very similar type of dynamics. So we sort of write evolution, but so here, this is evolution in imaginary time, but you write the same equation as evolution in real time of parameters, right? And I remind you that, again, it's not evolution of, say, just a Slater determinant state, as in, say, what Karina was showing to us. But this also involves evolution of the entanglement of how basically when the gap is changing, then the phonons will know about it, like even how electron and phonons will be entangled. Okay, so in the context of this photo-induced superconductivity, this is something that, okay, we're not ready to show yet, but I want to show you at least one example where this time-dependent transformation actually worked remarkably well. So, yes, okay, sorry. This is just trying to connect to what was in the official title. So let's take the familiar Kondo problem, right? You know that the Kondo problem is very complicated. Sorry, it's now something which is more in the domain of cold atoms. Okay, like it turns out you can realize a broad range of Kondo Hamiltonians with cold atoms, but the most natural experiments would be some kind of quenches. And in particular, the kind of quench that we were thinking about is that if you have a ferromagnetic Kondo and you suddenly prepare an impurity spin and you want to look at its dynamics. So, and the trouble, even in equilibrium, you know that if you're on the ferromagnetic side, at first, the kind of your interaction is irrelevant. You think that you are flowing to basically the regime where all the interactions switch off. But unfortunately, if you have anisotropy, then the system will pick up and become anti-ferromagnetic. So when we ask people who are experts in NRG whether we can collaborate with them to study dynamics in this regime at long times and low temperatures, they said, no way. I mean, basically, there are so many crossovers, so the best numerical approaches fail. OK, so then actually Tao used this variational approach, and actually it works, and it shows something quite remarkable. OK, since my time is up, let me just focus on this regime, right? So that's this AF2 again. So we start with the interactions which are really ferromagnetic. But then we know that in the sense of RG flow, the interactions, like if in equilibrium, right, if we do the usual RG steps, the system would discover first the interaction constant would flow to 0, but then it would become anti-ferromagnetic. So what this shows you is basically, so think about this is a space. So this is fermions, right? It's a function of distance to the electron. This is time. And we look at the part of the wave function that corresponds to impurity spin, which is up, right? So red means that the spin of electrons nearby is also up, and blue means that it's down. And you can see that at short times, right? So we just added an impurity spin. So fermions started by having a nice Fermi C, then they suddenly see the spin up pointing next to them. And you see that, oh, because it's ferromagnetic interaction, they align ferromagnetically. And of course, this means that you have an excess spin down component, and that's being emitted as a wave. And then if you wait some time, you see that something quite interesting happens, that basically even in real time, in quench dynamic, the system is doing the same thing as it does in equilibrium. It actually discovers that it wants to be anti-ferromagnetically correlated. And you see that at a later time, correlations switch from being ferromagnetic to anti-ferromagnetic. And of course, this requires some kind of spin imbalancing, and there is a way of kind of spins which is sent to infinity. So I think that this approach based on beyond Gaussian states is very powerful. So already in this example of well-studied Kondo, it can give us dynamics which I don't know how to get by any other means. And I think it's kind of promising to apply it to this non-equilibrium superconductors. OK, but so this is a summary of the main part of my talk. So I try to give you an argument that external driving can enhance electron-phonon interaction. It can be understood as parametric amplification and leads to increase of BCS coupling constant. But it has to compete with electrons becoming less coherent with extra scattering of electrons. But we find that there is a transient regime in which enhancement of BCS coupling dominates. And within this simple Hostin model, we find enhancement of the order of 150%. And I emphasize again that non-equilibrium Flaquet aspects are crucial. We cannot get the same physics just by looking at time-averaged quantities. Thank you.